So we've just added a new function to your bank of functions that you need to have as a pre-calculus student. Whenever you're doing graphs of exponential functions, there's a basic shape that you need to mentally associate with it. The usual shape for an exponential functions graph will look like this. The untransformed exponential function with a base that's greater than 1 will have a y-intercept at 0, 1. To the left of the y-intercept, the graph will get closer to its horizontal asymptote like this. To the right of the y-intercept, the graph will grow very, very steeply like this. So again, this is the basic shape for a function in this form. F of x equals a to the x, where a is a base that's greater than 1. A base like 2 to the x or 3 to the x, like the one we graphed in the previous video. So what you want to do is be able to apply transformations to a shape like this when graphing exponential functions that have a base like that. So keep in mind, transformations involve shifting left and right, shifting up and down, reflecting the graph about the x-axis or the y-axis, and in some cases stretching or shrinking the graph. The bulk of the transformations you'll see in the homework just involve shifting and reflecting. You don't see too many transformations involving stretching or shrinking. So using this as a basic reference, sort of a generic shape for all exponential functions with a base greater than 1, let's sketch a couple of graphs and use the graph to determine the information about the domain, the range, and the asymptote equation. So we are first asked to sketch the graph of the function y equals 3 to the negative x. So now when you're thinking of transformations, this transformation syncs up with this type of transformation. You have a negative x plugged into the function, and whenever that transformation is applied to something like this, that's a reflection about the y-axis. So what I'll need to do is, since that's a y-axis reflection, I want to take this shape, this sort of generic reference shape for an exponential function, and reflect it about the y-axis. Notice that'll keep the same y-intercept, so this function will still have a y-intercept at the point 0, 1. But reflecting it about the y-axis will take the asymptotic behavior, the part of the graph that gets closer and closer to the x-axis, and that'll reflect over here on the right end and get closer and closer and closer. And then the steep portion that represents your exponential growth will reflect over here on the left side. So things to remember about exponential functions. Remember, the domain represents the set of all inputs that you can plug in to an exponential function. Even though we've reflected this and transformed it, you can still plug any real number into an exponential. So the domain will always be all real numbers. The range is going to be established by where the asymptote falls. This asymptote falls at y equals 0, and all the y values are strictly above and never touching that y equals 0. So the range is parentheses 0 to infinity. So even though the graph was transformed, the original domain and range of an exponential function still applies, and the asymptote is still in the same position. The horizontal asymptote for this function is at the x-axis, so that means the equation for the asymptote is y equals 0. Okay. The transformation involved here, you're asked to sketch the graph of y equals 4 to the x minus 3. Even though we're using different bases, all exponential functions have this type of shape. The only subtle differences that are offered is the higher the base, the steeper the graph, and the closer it gets to the x-axis over here. So just to illustrate that for you on the calculator, you know, like again, I'm just sort of using this as a generic reference for all exponential functions. So if I just do a little comparison, the graph we did on the previous page was y equals 2 raised to the x. So you could type that in as 2 with the caret symbol and x, and that will graph in blue. And then let's just compare it to the graph of maybe this one, 4 raised to the x, just to see what subtle differences there are. So y equals 2 to the x will be graphed in blue, y equals 4 to the x will be graphed in red, and I'll do these in zoom decimal, zoom number 4. So again, the graph starts close to the x-axis, crosses the y-axis at 1, and then grows steeply. The red graph also close to the x-axis, a little bit below the blue graph, and then they touch the y-intercept, and then it grows steeply. So let me shift my window down a little bit. Let's see, I want to move the window down, so let's take y minimum. Let's add maybe about 3 to that, and add about 3 to the y value and y max. So then if I regraph it, it'll scoot the x-axis down a little, so you can see how both the blue graph and the red graph, when they're both graphed, they both still have this same basic shape. Asymptotic behavior over here on one side, crossing the y-axis at 0, 1, and then growing very steeply on the right. So even though I'm sort of using this as a reference for all exponential functions, this is still a very good picture for you to mentally pair with exponential functions graphs. So you don't necessarily have to plot any points. You can just use the transformations that you learned with this basic shape to create the new functions graphs. So in this one, I'm sketching the graph of y equals 4 to the x minus 3. So the transformation used here is taking a function f of x and minus 3 from it. That's going to be a vertical shift by 3 units down. So if I'm using this as my basic shape for all exponential functions, then I want to take this and move it down 3 units. So notice that the things you're going to make sure you do first is note the asymptote is sort of like a baseline for the exponential functions graph. If you do any vertical shifting, always make sure you accommodate the asymptote being moved first. So what I want to do is on my graph denote the fact that the asymptote that used to be at the x-axis is now being shifted down 3 units. So that means y equals negative 3 will be our asymptote equation in this case. And the intercept, we've only shifted it down. We're not moving it left or right. The intercept is always 1 unit away from that asymptote. So I'm essentially shifting this point down by 3 also. So that means your intercept's actually going to be at the point 0, negative 2. And then, again, without plotting any other specific points, just this sort of central point at the y-intercept and knowing where the asymptote falls, everything else is going to follow this same basic shape. The graph will get very close to the asymptote this direction and then grow very steeply in that direction. And so y equals 4 to the x minus 3 will look something like this. And by all means, double check it on the calculator if you want to compare the two together. So let me clear the old graphs out. 4 raised to the x and then minus 3. Graph that in blue. And then if I graph it in zoom 4, there's the asymptotic behavior. It looks almost like a flat line at y equals 3. Don't be deceived by this. The graph never actually touches the asymptote at y equals negative 3. It's just very, very, very close to it. And then you can see it crosses the y-axis at the 0, negative 2 point. That's always going to be 1 unit away from where your asymptote falls. And there's that steep growth that represents how rapidly an exponential function grows. So our domain didn't change. None of the transformations that we do here in pre-calculus will change the domain of an exponential function. That'll always be all real numbers. And again, try to not get caught in the trap of thinking this means vertical asymptote right here. That's just very rapid growth. This growth is so steep it looks like it has a vertical asymptote, but it does not. The range of the function, since we shifted the original graph down by 3, then that means you're going to use the asymptote as a baseline for the range. It'll start at the y value negative 3, not included, again, because it's an asymptote, and going to infinity, like so. Okay, so now coming up next, I'm going to introduce you to probably here's the note about it, the perfect exponential base, the base e. That's the next video.